Clone graph. If you want to ace technical interviews at FONG and beyond, clone graph is a classic you must master. This pattern mastery 100 essential tests whether you truly understand recursion, graph traversal, and deep copying data structures. Did you know that a significant portion of candidates lose points here by shallow copying nodes, missing cycles, or failing to preserve graph structure? By getting this one right, you'll stand out in any interview and be ready for a whole family of graph problems. Here's the breakdown. You're given a node from a connected undirected graph, where each node contains a value and a list of neighbors. Your job? Return a deep clone of the graph, a new set of nodes, with the same structure and connections as the original, but no shared nodes. You can't just return the same nodes or rewire incorrectly. Cycles and shared neighbors make this tricky, so you need to carefully manage which nodes you've already cloned. Let's assess the challenges. Graphs can have cycles, so a naive recursive or iterative copy may loop forever. Nodes might be shared among neighbors. If you clone each node multiple times, the structure gets corrupted. We need a way to remember which nodes we've already cloned, so we can reuse the correct references. Use a hash map, dictionary, to track each original node and its corresponding clone. Traverse the graph, BFS or DFS. For each node, if it hasn't been cloned, make a new node and put it in the map. Then, recursively/iteratively clone all its neighbors. Here's our plan. Edge case. If the input node is none, return none. Create a map, old to new equals, to track original to clone nodes. Define a helper, DFS or BFS. If a node is already in the map, return its clone. Otherwise, clone the node, add it to the map, and recursively clone all neighbors. Return the clone for the input node. Approach, DFS recursion. Time complexity, O(n plus m), where n equals number of nodes and m equals number of edges. This line imports Java's utility tools, like map, hash map, and collections we'll use to store and manage data. This defines the solution class, the container where our graph cloning logic will live. This comment tells us the purpose of the next line. We're going to store which original nodes we've already processed, and the cloned version we created for them. Here we create a visited map. The key is an original graph node, and the value is its cloned copy. This prevents us from cloning the same node multiple times, and it also helps us handle cycles in the graph. This is the main method. It receives a starting node from a graph and returns a completely cloned graph, meaning a new set of nodes with the same connections. This handles an edge case. If the input graph is empty, no starting node, there's nothing to clone, so we return null. This line begins the cloning process using DFS, depth first search. It hands the work to our helper method that does the real cloning. This closes the clone graph method. This defines the DFS helper function. It takes one node, clones it if needed, and also clones everything connected to it. This comment explains a very important rule. If we've already cloned this node earlier, we don't redo the work, we just reuse the existing clone. This checks the map to see if the current node has already been visited and cloned. If it has been cloned already, we immediately return the clone from the map. Pause. This is what prevents infinite loops when the graph has cycles. This closes that early return block. This comment tells us we're about to create a brand new copy of the current node. Here we create the cloned node. We copy the value node.val, but note, the neighbors list will be filled in next. We're building the connections step by step. Now we store the mapping from original node to cloned node in visited. This is crucial because neighbors might point back to this node later, and we'll need the clone ready. This comment signals the next part. We're going to clone every neighbor connected to this node. This loop goes through each neighbor of the current node. Think of it like, for every node I'm connected to, I also need to create a cloned connection. This line is doing two things at once. It calls DFS neighbor to get the cloned version of that neighbor, creating it if needed. It adds that cloned neighbor into the cloned node's neighbors list. So we're rebuilding the same graph connections, but using cloned nodes. This closes the neighbors loop. After cloning the node and all its reachable neighbors, we return the clone back to the caller. This closes the DFS method, and this closes the class. Final wrap-up. And that's how this algorithm works. It first checks and stores clone nodes to avoid repeats, then uses DFS to recreate every neighbor connection until the entire graph is duplicated. Efficient, simple, and elegant. Test case check. Clone graph using DFS. Let's test our function using this input. 2, 4, 1, 3. 2, 4, 1, 3. These lists represent the neighbors of each node in the graph. For example, node 1 connects to nodes 2 and 4, node 2 connects to nodes 1 and 3, and so on. Here's why the solution works. We perform a DFS traversal of the graph. Whenever we encounter a node, we create a copy of it and store the mapping in a dictionary. Then we recursively clone each of its neighbors. If we revisit a node we've already cloned, we simply return the existing copy, preventing infinite loops in cyclic graphs. And that's exactly what our program outputs: 2, 4, 1, 3. 2, 4, 1, 3. It perfectly matches the expected clone structure, confirming that the graph has been duplicated accurately. Wrap up. So, our implementation is correct. The algorithm successfully creates a full deep copy of the graph using DFS and a hash map, efficient, accurate, and reliable. Approach: BFS iterative. Time complexity: O(n plus m). This line defines the solution class. It's simply the container where our graph cloning logic lives. Here we define the clone graph method. It takes a graph node as input and returns a deep copy of the entire graph starting from that node. This is a safety check. If the input graph is empty, there's nothing to clone, so we return null immediately. This line creates a map that links each original node to its cloned version. Think of it as a translation table. Original node on the left, cloned node on the right. Here we create a queue to perform BFS. BFS lets us traverse the graph level by level without missing any connected nodes. This creates a clone of the starting node and stores it in the map. At this point, the clone exists, but it has no neighbors yet. This adds the original starting node to the queue so BFS can begin from there. This starts the BFS loop. As long as there are nodes waiting to be processed, we keep traversing the graph. Since each node and edge is visited once, the time complexity is O(n plus m). This removes the front node from the queue and stores it in cur. This is the current node we're cloning connections for. This loop iterates through all neighbors of the current node. These neighbors represent edges in the graph. Here we check whether this neighbor has already been cloned. If it hasn't, we need to create its clone. This line creates a clone of the neighbor node and stores it in the map. Now we add the neighbor to the queue so BFS will later process its neighbors as well. This closes the condition that handles newly discovered nodes. This line connects the cloned version of the current node to the cloned version of its neighbor. This is how we rebuild the graph's edges in the cloned graph. This closes the loop over the current node's neighbors. This closes the BFS loop. At this point, every reachable node has been cloned and fully connected. Finally, we return the cloned version of the original starting node. This gives us access to the entire cloned graph. This closes the method. And this final brace closes the class. Final wrap-up. And that's how this algorithm works. It first creates a clone of the starting node and a mapping structure, then uses BFS to traverse the graph while cloning nodes and reconnecting their neighbors. Efficient, simple, and elegant. Test case check. Clone graph using BFS. Let's test our function using this input. This represents a graph with just one node, and that node has no neighbors. In other words, it's a single isolated node with an empty adjacency list. Here's why the solution works. We start by cloning the initial node and placing it in a BFS queue. Then we process the queue level by level. For each node, we look at all its neighbors. If a neighbor hasn't been cloned yet, we create it and push it into the queue. Then we connect the cloned node to its cloned neighbors. And that's exactly what our program outputs. This confirms that the BFS cloning logic works correctly even for the smallest possible graph. Wrap up. So, our implementation is correct. The algorithm successfully clones the graph, even in minimal cases, using a clean BFS traversal and a mapping of original to cloned nodes. Efficient, accurate, and reliable. Clone graph. Let's do a recap. So, we just tackled one of the trickiest graph problems in interviews, clone graph. It's a true test of your understanding of recursion, traversal, and deep copying complex structures. Once you master this, you'll be ready for an entire class of graph and network-related problems that interviewers love to ask. Breakdown recap. At its core, this problem asks us to create a deep copy of a connected graph, meaning we build entirely new nodes that mirror the original connections perfectly. The catch? Graphs can contain cycles, so careless recursion can loop forever or duplicate nodes. Assess recap. We compared possible approaches. Brute force copying fails because of repeated nodes, while using recursion with memory tracking works beautifully. The key insight was to use a hash map to store already cloned nodes, so every original node maps to exactly one copy. This ensures no duplication and handles cycles cleanly. Structure recap. Our plan was simple yet powerful. Handle the base case when the graph is empty. Use DFS to explore and clone each node. Store each clone in the map, then recursively connect its neighbors. That's it. A clean, recursive structure that mirrors the graph one layer at a time. Implement recap. We implemented the DFS-based solution, ran it through LeetCode, and it executed flawlessly. No infinite loops, no shallow copies, and no structural mismatches. The cloned graph preserved every connection while remaining fully independent of the original. Check recap. After running multiple test cases, the cloned adjacency lists matched perfectly. All cycles, neighbor relationships, and node values aligned as expected. All test cases passed with optimal performance. Closing insight. The big takeaway? Clone graph is all about thinking recursively, breaking complex structures into smaller, familiar problems. Once you grasp how to track references and prevent duplication, you unlock the mindset needed for tackling any advanced graph or tree problem in technical interviews.